Denial of service tools. Kali Linux. Armin Shariarian. Denial of service tools. Denial of service is not the same as stress testing. The objective may be different. When it comes to the two sets of tools being used, stress testing is commonly done by development tools to be able to provide performance metrics. It is used to determine the functionality of a program or system under stress, whether it's the stress of vol. UME or the stress of malformed messages. There is a fine line, though. In some cases, stress testing will cause a failure of the application or the operating system. This will result in a denial of service attack. However, stress testing may also just lead to CPU or memory spikes. These are also valuable findings, since this would be an opportunity to improve the programming. CPU or memory spikes are bugs, and bugs should be eradicated. What we are looking at in this section will be programs that are specified Kali developed for the purpose of knocking over services. Slow loris attack. Much like the SYN flood that intends to fill up the partial connection queue, there are attacks that will do similar things to a web server. Applications don't necessarily have unlimited resources at their disposal. Often there are caps on the connections the application server will take on. This depends on how the application is designed, and not all web servers are susceptible to these attacks. One thing to note here is that embedded devices often have limited resources when it comes to their memory and processor. Think about any device that has a web server for remote management. Your wireless access point, your cable modem/router, a printer. These devices have web servers to make management easier, but the primary purpose of these devices isn't to provide web services, it's to act as a wireless access point, a cable modem/router, or a printer. The resources for these devices will be primarily applied to the device's intended function. These devices are one place to use this sort of testing, because they simply won't expect a lot of connections. This means that an attack such as Slow loris may be able to take these servers offline, denying service to anyone else who may try to connect. The Slow loris attack is designed to hold a lot of connections open to a web server. The difference between this attack and a flooding attack is this is a slow play attack. It's not a flood. Instead, the attack tool holds the connection open by sending small amounts of data over a long period of time. The server will maintain these connections as long as the attack tool continues to send even small amounts of data, partial requests that never quite get completed. Slow loris is not the only type of attack that goes after web servers, though. In recent years, there have been a few vulnerabilities that go after web servers. Another one is Apache Killer, which sends bytes in chunks that overlap. The web server, in trying to put the chunks together, eventually runs out of memory trying to make it work correctly. This was a vulnerability found in both the 1.x and 2.x versions of Apache. One program that Kali has available is slowhtest. Using slowhtest, you can launch one of 4 HTTP attacks at your target. The first is a slow headers attack, otherwise known as Slow loris, as noted previously. The second is a slow body attack, otherwise known as Are You Dead Yet? The range attack, known as Apache Killer, is also available, as is a slow read attack. All of these are essentially the reverse of the flooding attacks discussed earlier, in that they accomplish the denial of service with a limited number of network messages. In example 2 to 7, the default slow headers attack, Slow Loris, was run against Apache on my Kali box. No traffic has left my system, and you can see that after the 26th second, the test ended with no connections left available. Of course, this was a simply configured web server with very few threads configured. A web application with multiple web servers available to manage load would survive considerably longer, if they were available at all. Example 2 to 7. Slow output. The Apache server targeted here uses multiple child processes and multiple threads to handle requests. Caps are set in the Apache configuration. The default here is 2 servers, a thread limit of 64, 25 threads per child, and a maximum of 150 request workers. As soon as the number of connections available was maxed out by slow test, the number of Apache processes was 54 on this system. That would be 53 child processes and a master or parent process. To handle the number of connections required for the requests being made, Apache spawned multiple children and would have had multiple threads per child. That's a lot of processes that have been started up. Considering that the Apache server that was running was completely up to date at the time of this writing, it seems clear that these types of attacks can be successful, in spite of how many years they have been around. Of course, as noted earlier, that entirely depends on the architecture of the site. SSL-based stress testing. Another resource-based attack that isn't about bandwidth, but instead is about processor utilization, targets the processing requirements for encryption. For a long time, e-commerce sites have used Secure Sockets Layer, SSL, or Transport Layer Security, TLS, to maintain encryption between the client and the server in order to ensure the privacy of all communication. These days, many servers use SSL/TLS as a matter of course. If you attempt to search at Google, you will see that it is encrypted by default. Similarly, many other large sites, such as Microsoft and Apple, encrypt all traffic by default. If you try to visit the site by using an unencrypted uniform resource locator URL, by specifying http:// instead of https://, you would find that the server converts the connection automatically to HTTPS for you. The thing about SSL/TLS, though, is that encryption requires processing power. Modern processors are more than capable of keeping up with normal encryption loads, especially as modern encryption algorithms are generally efficient with processor utilization. However, any server that uses SSL/TLS incurs a lot of processing overhead. First, the messages that are sent from the server are generally larger, which means that it takes more processing to encrypt those larger messages than the comparably small messages originating from a client. Additionally, the client system is probably sending only a few messages at a time, whereas the server is expected to be encrypting messages to a number of concurrent clients, which may all have multiple concurrent connections going to the server. The load primarily comes from the creation of the keys that are needed to encrypt the session. Capabilities exist in Kali to target outdated services and capabilities. The problem is that some of these long superseded programs still remain in service in a lot of places. As a result, it's still important to be able to test them. One of those services is the SSL encryption. The final denial of service testing program will look at here targets. Servers that use SSL. SSL is generally no longer in use, having been supplanted by better technology, but that's not to say that you won't run across one. The program THC-SSL-DOS targets servers based on the idea that encryption is computationally expensive, especially on the server side. Example 2-8 shows a run of THC-SSL-DOS against a server that has been configured to use SSL. However, the issues with SSL have been known for so long that the underlying libraries often have SSL disabled. In spite of running against an older installation, you can see that the program was unable to achieve a complete SSL handshake. However, if you were to find a server that did have SSL configured, you would be able to test whether it was vulnerable to a denial of service. Example 2-8. SSL-DOS using THC-SSL-DOS utility. Root at Rosebud #THCSSL-DOS L100.168.86.239.443 accept. This failure highlights one of the challenges of doing security testing. Finding vulnerabilities can be hard. Exploiting known vulnerabilities can also be hard. This is one reason that modern attacks commonly use social engineering to make use of humans and their tendency toward trust and behaviors that can lead to exploitation. Often, technical vulnerabilities are harder to exploit than manipulating people. This does not mean that these non-human issues are not possible given the number of vulnerabilities discovered and announced on a regular basis. See BugTrack and the Common Vulnerabilities and Exposures Project for evidence of this. DHCP attacks. The Dynamic Host Configuration Protocol, DHCP, has a test program called DHCPig, which is another consumption attack, designed to exhaust resources available in a DHCP server. Since the DHCP server hands out IP addresses and other IP configuration, it would be a problem for enterprises if their workers weren't able to obtain addresses. While it's not uncommon for the DHCP server to hand out addresses with long leases, the period of time a client can use the address without having to renew it, a lot of DHCP servers have short lease times. A short lease time is important when everyone is mobile, as users come on and off the network regularly. Sometimes staying for short periods of time, having clients hang on to leases can also consume those resources. What this means, though, is that when clients have short leases, a tool like DHCPig can grab expiring leases before the client can get them, leaving the clients out in the cold without an address and unable to do anything on the network. Running DHCPig is as simple as running the Python script pig.py and specifying the interface that is on the network you want to test.